So good afternoon, everyone. Welcome to to the third lecture of this mini school. My name is Francesco Petroccione, and I'm the interim director of NITheCS. And today I have the pleasure of introducing Dr. Xifeng Ruan from WITS, who will give us the first of two lectures on really practical hands-on implementations of machine learning for applications in high energy physics. Yeah? And because of a commitment of Professor Bruce Mellado, we swapped the order of the lectures so that we will first have the two lectures on practical hands-on machine learning. And the last lecture will then be delivered by Professor Bruce Mellado and will be more about the big data aspect of high energy physics. So, Xifeng, you already started sharing the screen with the relevant libraries that I hope all participants have already installed on their computers. If you would like to start your presentation or your interactive session, we are all very curious to see what to hear and see what you have to share with us. And if the participants, as usual, are welcome to use the Q&A facility to ask questions. If you have very urgent questions, just raise your hands and we can always make a plan to give you the right to speak. Yeah. So please, Dr. Ruan, if you would like to start, you're most welcome.
Okay, thank you, Francisco. So I'm going to start. So hello, everyone. So my name is Xifeng Ruan, as already been introduced here. So I'm a physicist in the particle physics. So today I'm going to introduce this very simple hands-on session about how to use the machine learning techniques in the high energy physics analysis. But actually, this is not restricted in the high energy physics field. So because I'm going to pay more attention on how to understand the whole procedure of the analysis. And we're using very little knowledge from the physics part, but pay more attention on the on how to build the machine learning framework and understand how it works. So just because this is a hands-on session, is not a lecture. So what you can do is that if you have any question, you can just stop me or raise your hand. I will see, and then I will explain. So before we start, I'm going to ask you bad audio reception. Can people hear me clearly? Can people hear me clearly?
Yes, so far so good. Yeah.
Okay. Okay. Good. So before I start, yesterday I think a PDF file has been shared to everyone. That's about how you install that this software is called the Anaconda. If you install that and follow that the instruction in the PDF, then you're supposed to see interface like this one, and then you click this launch under this Jupyter Lab, and then in your browser, it's Chrome or any other browser, you can see just one index page here, and it's structured like this. So at the beginning, it should be more like this one, and then you should download that all of the files that are listed in the PDF file, and open them in the left sidebar. So this actually needs 3 files here. One is just this single notebook file, and then another 2, they are just the data sets. So because we are going to use these data sets as an example to show all of the study. So one of the data sets is a signal, one of this background. So here I'm going to, before I start, I'm going to ask if everyone, you have any difficulties to download these 3 files. So you can ignore the last one, the 3 files. And if you can successfully open your browser and see that the same page as what I have now. Yeah. So if anyone has a problem to open this file and to see the similar page as what I do, then please tell me. I see one person has raised a hand. Okay. I don't know if you raise your hand if you can type anything. Talking permitted. Okay. Hello, Musa. Anything to say? I think you're muted. You can unmute yourself, Musa, and yeah, I see. Hello. If you have any questions, you can also type in the chat box. I will see. Okay, so here I assume that everyone has downloaded downloaded the 3 files. The major file is that this notebook, and then 2 of them, the other, they're the data set. One is a signal data set, one is a background data set. Okay, and then you should open that this what's the name? The Anaconda, this software, and open this the notebook within your browser, and you can see what I have now. So basically what we are going to do is just to run everything that's on this page in this notebook, what you can see here. To run them, that you can click that this triangle button, if you can see my cursor. This is to run step by step, and then this one you can run from the beginning to the end. So basically you will just use these 2 buttons to run what you have now in this notebook. Okay, now I'm going to start now. So I'm going to start. So basically that the task, also the objective of this hands-on session is to show an example of the simplest event classification, or in other words, it's anomaly detection in the high energy physics. But as I mentioned, this is not only restricted in the high energy physics. This actually the principle is the same for all of the similar questions for the all the similar objectives. Yeah. So here what we are going to show is just a 2-category classification. So 2-category, that means you have you're going to split your data set to be either the good and the bad, or the bad, or we in high energy physics we call them the signal and the background. So the signal events, they are the events that you want to keep. You want to keep in your after your selection, and for the background is that the events you want to discard. So your objective, also your target, is that to separate the signal and the background as much as possible, and keep as much as possible the signal, and reject as much as possible the background. So of course that this cannot be 100% achieved. So this is why we're going to use a machine learning, because you always have some kind of mixing and confusion. So then the machine learning is to help you to get the maximum performance, to keep the signal and reject the background, or keep the events you want, reject the events you don't want. Okay, so now we are going to move to so these blocks. So basically you can see that these blocks, that is a code in the blocks, there is a code will be run. They are written in the Python programming language. And of course that doing machine learning is not restricted in the Python language, but this is one of the simplest case here. And then to run them, you can just simply just click one of the block and then click this small triangle, and it will run. And you see the star that is running. Once it turns to the numbers, that means it's finished. The run has been finished. Okay, because the first block is just to import all of the necessary libraries that in the Python that you are going to be used. They are going to be used in the following analysis. So this is very quick. There's nothing important is done here, just to tell that the code where are the packages that I'm going to use a bit further. Okay, so now we just go to the second place here, reading the data. So before we do the analysis, we have to read in the data set, because the data set is the most important thing. We're going to tell that the machine learning classifier that what data set they should look at and how the signal look like, how the background look like, so that the classifier can know that how to set up the criteria to distinguish the signal and the background. So basically, actually inside the classifier is tuning all of the weights. So the first step we're going to do is just to read in the data in your code. So as we mentioned that we are doing this two category classification. It's not as complicated as other situation that you have 10 or more categories. So just two categories. You have one category to keep, one category to reject. So what you should do here is that we just import the signal data set and the background data set. So because the files that you download from my Google Drive, they're saved in the TXT format. Actually, it's a CSV, the comma separated file, a comma separate value format. So you can use this read CSV function to read in the signal and the background in the same time. So here I'm going to ask you to check is that you need to change that this path, what I'm selecting, to the path that where you download this signal.txt and the background.txt, because when you download that, you possibly put these files in different places, and you need to be careful if you are using the Windows machine that you should use that slash, the other side, the slash, okay, and not because I'm using the Mac machine and also it's similar as a Linux system, so I use this I don't know if it's anti-slash. The other one is anti-slash. You need to use the other side. So I hope that you, this has been, I have mentioned that in the PDF file that's sent by yesterday. So I hope that you have successfully read in the signal and background data set in your local computer, use the proper path. So you need to put this path to be the proper one that you download these files. Or if you don't want to bother with that, you can just put this file, this signal.txt and background.txt in the same place that where you save this file. So then you don't need these slashes, you just directly call the signal or the background.txt. So then you call the signal.shape and the background.shape here. You just run this block. It will tell you that how many rows it has and how many columns it has. So this two number tells you that for the signal file, it has 5,451 rows and 104 columns. And for the background, it's the same number of columns, but much more events, or say rows, it has 87. So if you see that these two numbers here, that means you successfully read in the signal and the background data set. Okay. Yeah. So that means the file was successfully loaded. So here I'm going to ask people if you reach to this place successfully or you have any problem. If you have any problem, you can just type in the chat box. Okay, yeah, I should give you some time. Because it's a hands-on session, so we should have some interactive communication. And I'm not going to just read all of the things that's on this notebook, rather than just to interact with you. And if you have questions, I will answer your question and instruct you how to reach what I'm doing, achieve what I'm doing. But maybe it will be slightly different if you're using a Windows machine. Or different Linux machine. Yeah. Don't worry. So I think that at this step would be the most difficult one, because this really depends on how you put your file, how you be familiar with this software, how you read and load in all of the files. After this step, if you can successfully see this line, this number of rows and number of columns, then the following things will be much easier. There's no obstacles at all. So just this step that you possibly have some problem to type in the correct path to load these files. what I suggest you to do is that you put the 3 files that we downloaded from the PDF I sent yesterday, these 3 files in the same folder. And then you just go to the folder that you are, you put these 3 files, and then you can just double click this supervised bdt.ipymb, this notebook file. And then you can see this interface, all of this content. Then here you even don't need the path. You can just directly put the signal.txt and background.txt. Yeah. Which step? Oh, this question. I'm not sure this is if this is relevant to you are typing the correct path. So firstly, Dimakatso, have you successfully reached the first step? You can successfully load all of the library, right? Just this syntax error only happens in the second step or not? Yeah, library, okay. Yeah, then it's just this step. So maybe this is a path problem. I don't know. You successfully download the 2 files, right? The signal.txt, background.txt. You can put them, yeah, you can put these 2 files same folder as this supervised bdt.something. And then you don't need to type this path. You just directly type the signal.txt or background.txt. For example, if I delete this, I'm not going to use the path. I'm trying to do here is I directly type the 2 files. As long as you put them in the same folder, I suppose it should work. Yeah, it should work. Yeah. You can either use the absolute path or just simply type the file name if you put these 2 files under the same folder. Okay, great. That's great. So I hope that everyone just successfully reached this step, because this possibly different people, different machine has some problem. And
Xifeng, there is a question by Noko. I will just allow to talk. So please, Noko, you're welcome to unmute yourself and ask the question.
Yeah. Hi, Noko.
Yeah, no, it's like with Musa earlier. Here, hello, hi.
Oh, it's okay. I just wanted to ask something, but yeah, it's sorted right now. It's fine.
Okay, great. Okay, thank you. Yeah. Okay. So then we just move to the next step. So firstly, here I just say, when you reach this step successfully, you successfully read in the signal and the background data set. So as you have learned that from the previous Deepak's lecture, that you know that the purpose is that we are going to use the signal and the background data set to train the classifier, to tell the classifier what feature looks more like signal and what feature looks more like background. Then after the training, we set up the classifier, a new data set, which is a known data set. That means we don't know which is signal and background come in. Then we can use this classifier to distinguish or to tell us this unknown data set as more signal-like or background-like. So now what we are going to do is this step. Okay, so the next block, if you go to the block 3, 4, so here is we are doing nothing here. It's just to show you that how that this data set, the signal data set and background data set looks like. So you type the signal dot head, you can just run them, and the background dot head. It just show the first 5 rows and the different columns. Of course, that there are 104 columns that you couldn't just show all of them. So here just show for each column that it has a variable name in the first row, and then it has different values. So this variable name, you don't need to bother that what they mean. For example, sometimes like this MET, it can mean the missing energy, transverse energy. This is a terminology in the high energy physics or particle physics. But actually, for the machine learning part, it doesn't matter that you know the meaning of or not for time being. So what you should know is just like the structure, how that this CSV file looks like. Basically, that is the first row, just save the feature name. It can, if you do a different task, it's not a high energy physics, not a particle physics task. For example, you can put the human's height, the weight, the age, or anything that's here. Okay, so each column just represent a feature of this data set, or in our field, we say the variable. Usually in the general machine learning things, they say the feature. Okay, and each row, the different row just represent a different entry. Or say we say the events or the entry. So you can have the first collision, the second collision, the third collision. The collision is like it's the particle collision that in the LHC, the Hadron Collider. Okay. So yeah, so here that each row just represent the different events, different cases, different entry or the different collision, and each column just represent a different feature. Another thing I'm going to mention here is that you see these values that they vary a lot. So for example, like this weight, it can have this weight column, it can have very tiny number, 8 times 10 to minus 10. And you can have the integers and all just a regular float number, and it can vary from in a large range, like 18,000 to just 2 point something or minus 83. So you can have anything, and sometimes you can have a lot of the value is 0, and some value is as like 29, like this. Okay, so this just to show you how that the signal data set looks like, and in the same time, similarly, you can see the background. It's also similar. Okay. Now the block 5 and the block 6, here what we are doing is just check if we have any the duplicated lines, but because that these two files are prepared by me, very well prepared by me, so and I can ensure that there's no duplicates, but we still just do this kind of check to see if there's two rows, they are exactly the same, then you possibly want to keep or to remove the duplicates. But because that these data sets are well prepared, so we don't have such case. But I just show you that there's such functionality. So possibly just click here and just run them. Okay. So now we reach the block 7. Now we can go to the block 9 and 10 for both the signal and the background data set. So here we are trying to check if any of the value. So the value that means any of this number for a particular event, no, sorry, not this table. Any of this number in a particular events in a particular feature, which show you a null NaN number. So we want to remove that these physical values, because these two data sets are well prepared, as I mentioned. So we don't have such kind of value that in the data set. So, but we just do some safety check here. But if you're doing some other task, other analysis, not always ensure that your data set is perfect. You always can have the chances that you have empty cells, you have a cell which has the NaN or the null number, etc. So this is can be very say often to see if you are doing a machine learning analysis. So that's here what I'm trying to emphasize is that before you do any study, you need to clean up the data set very carefully. You need to make sure that the data set you have the valid value, the float integers, or just a true or false, this bool value that you as your expectation. Okay, so you just do this cleaning. Let me see that we have some Q&A here. What would you do missing value otherwise, apart from rejecting them? So it depends on the concrete task, what you are doing. As you said that, for example, assume that you are sure that the missing value is not going to say bias your data set, then possibly, and also you have enough data set to do your training, you can just reject them, throw them away. And sometimes that you want to use a part of the feature of your and of this part of a problematic data set, but you also your lack of the events, you don't want to waste the data set. Sometimes you set them set up some default value in this data set, but you have to be very careful if the default value will not bring in any discriminant power to your signal in the background. So it just depends on what concrete problem you are studying. Okay. Usually that if your data set is a large amount and very perfect, and you just have some kind of random bad value, you can just throw the events away. But if there's a huge amount of them, then you have to consider very carefully. Yeah. Okay, now, so till now that we haven't done anything complicated, anything which is difficult to understand. It's just say the dirtiest work in the machine learning analysis is called the data cleaning. That if you go to the companies, that you will find that you spend a lot of time on this stuff, because that if you collect the data from not from the particle physics, you collect data from the marketing, from the internet, that most of the data set they need to be cleaned, because the people always fill in some kind of physical value, the value you don't want, or just some random false value. So you have to be very careful about that. Now here on the, I think here it's, I don't know why it's called block 7. Yeah, okay, it's block 10, yeah. Statistical description. So here just to show some kind of summary of data set. Again, this is nothing, we are doing nothing here. What we are doing is just to show that these variables, the distribution, like the maximum value, the minimum value, and the 25, 15, 75 percentile, and also the standard deviation and the mean value. So this is just to give you some feeling. For example, if you see this table, which shows the first 5 rows of the events, but this may not give you the maximum and the minimum value. So in many cases, you could have the situation that the maximum or the minimum value is infinite, and those values you don't want. You want to throw them away. So from this kind of statistical check, then you can just see that if you have an infinite large number, it will show you here in the maximum place. If you have a negative infinite number, it will show you here. So this just also help you to check if the distribution looks okay, if you have a super huge standard deviation, if your mean value is significantly deviated from your expectation, and also if you have the outliers, which has a super huge, super small number. Okay, so here is just, it also gives you the type of the value. It could be even a string, a Boolean, integer, or float number. Okay, so here these 2 blocks, the 10 and 11, it just show you some kind of statistical information of each of the feature, or say each of the variable. Okay. Still not many difficult things here. And then here in the block 12 and the following, that we are going to formally start the analysis. So because, as I mentioned, that actually if you import this data set, you will find you have 104 columns. So you have 104 different features. But for this analysis, that I'm not going to use all of them, that will take quite a long time for the training. So I'm going to use 1, 2, 3, 4, 5, 6, 7 features, or the 7 variables to proceed the training. Just illustrate the problem and how the procedure is done. So about the choice of these features, of course, that if your classifier is strong enough, you are using a lot of layer of the neural network, that you can use as much as possible the features. But that may not give you the best efficiency, because it takes you a lot of time for the training, a few hours, and maybe the result is no significant different from that you only use the 7 of them. So the choice of these variables depends on your understanding of the physics problem, or say your understanding of the your objective. If you're using a marketing model, not analyzing the physics data, you are analyzing the marketing data. So the choice of the variables depend on your knowledge of the marketing. So this is to say that why it's very important that for the people who are doing machine learning, who also should have some kind of understanding of the objective they're doing. So that helps them that quickly select the most important variable, which can help you to differentiate your signal and the background as much as possible. Yeah. So here, I just use my expertise to select 7 variables here. So you have to set up the 7 variables exactly same for your signal and background, because otherwise the classifier can 100% differentiate them if you use different variables. So you will see that, yeah, the sequence and also the variable name, or the feature name, has to be same for both the signal and background. So after the block 13, this block, you will define a new data set. It's called the pre-signal or the pre-background. So pre here means pre-selection. So this data set will be much smaller than the original signal and background data set. So if you type that to the shape and head here, it will show you what it looks like here. So you will find that it will keep that the same number of rows, because you select all of the events, keep the same number of rows, but it will only record 7 columns. It will only record 7 columns. So this step is trying to filter that 7 columns from the 104 columns. Select the variable, the only useful variable you think is useful variable, and keep all of the events, all of the rows. Okay. Yeah. Any question here? Because here we are going into the real analysis now. Yeah. So I don't see any question here. Now we just move to the next block. This is the block 14, if you run it, block 14. So in the block 14, what we are trying to do here is that we make some kind of selection of the rows, the events, rather than the columns. So among this pre-signal or the pre-background data set, which contains like for the background, it contains 88,000 of the rows and 7 columns. But now we still feel that we don't need that 88,000 rows, because obviously some of the events is not, we are not interested in them. So before we do any of the machine learning analysis, we can already just throw away some of the events, significantly reduce the number of background based on our knowledge of the physics. For example, here what I'm trying to do is that I say that for the pre-signal data set, pre-selected signal data set, for the missing ET significance, this is a variable of the missing transverse energy, a complicated variable of missing transverse energy. You don't need to worry about what the physical meaning of it. It's just like a kind of a feature. And then we say we only select that the events between the value of from 3.5 to 100. So actually you can see that the METSIG, missing ET significance, this variable, it varies from, you can have this value 2.3, 2.1, 2.1, 4.0, 2.1, and 3.7. So from my physics knowledge, I say that obviously that the events which has a value missing ET significance smaller than 3.5 is a value I don't want. And that reducing this kind of value for both the signal and background will not harm the signal, but can significantly reject the background. So then I can just do this selection in the same time for both the signal and the background. For both the data sets, any events which this feature, METSIG, whose value is smaller than 3.5, will be rejected, or say discarded. Then after this manipulation, I print the data set again because I just do this selection and I overwrite the pre-signal, pre-background data set. Then I just show what is content of these two data set, and you can see here. Now for the pre-signal data set, I have 1,310 rows and 7 columns. And for the background, I have 16,000 rows and 7 columns. And before I do so, how much I have? Before I do so, I remember at the beginning I printed that the data set, right? I have 5,000 of the rows for the signal and 104 for the background, for the column, for the features, and 88,000 of events for the background and 100 for the features. Now I just significantly, after these 2 steps, I significantly reduce the size of the data set to be a much smaller number of events, and a much smaller number of features. So this can significantly speed up your training, because we know that if we have 100 variables, that's going to take a long time to do a very complicated training. Okay. Any questions here? So what we are trying to do here, we still haven't reached the step of the training yet. What we are trying to do here is just to say shrink or say filter or say slim the data set in both 2 dimensions. One is to reduce the number of features, one is to reduce the number of rows based on the knowledge of the physics. Okay, now before doing so, before doing the real training, we are going to have a look at that the distribution of the signal and background, because we need to know that why that these 7 features we are using can differentiate the signal and background. Obviously, if these 7 features, they look all the same for the signal and background, then we can do almost nothing to differentiate these 2 data set. So in this block, this is called the block 15. So you don't need to change anything here, you just press enter. It will just draw the distribution, the 1-dimensional distribution for the signal and the background. So the signal shown in the blue and the background shown in the red here. And for these 7 variables or the 7 features that you can see, some of them, for example, this one, the stratify YY that shows the gamma 2 photon, stratify of the 2 photon. Some of them it has a very tiny difference, but in general, there's not so much difference. Some 2 photon, you can see the background always located in the very left side, and the signal has a longer tail. So this gives you some differentiate power, discriminate power to differentiate the signal and background. And like this MET-seq seems not too much difference, but the number of jet, the number of central jet, they are slightly different. So if you look at these variables, you will see some of them they are same, some of them they are not. They have some kind of differences. So the purpose of the machine learning is try to exploit all of these 7 1-dimensional figure of these features to exploit the difference between the signal background in these 7 features, and in the same time exploit the difference of the correlation, later we are going to mention, and try to make the best discriminating power, or say separation, between the signal and the background. Okay. So here, why we are going to see this 1-dimensional histogram. So what we are trying to do is understand, before we do the machine learning, if we already know why we are choosing these variables, if this variable can provide you the discriminating power. As I mentioned, if you see 7 of them in the same time, they're all just overlapping like this one, then possibly you have a feeling that it's not very easy to discriminate the 2 data sets, because the features you're choosing are so alike. Okay. Now let's just move to the next block. Here is another plotting block. So the block 16 and 17, what I'm trying to do here is just to draw the correlation matrix. So just now we have drawn the one-dimension histogram to differentiate the signal and background in the 7 features. But here we are trying to show is that you could have differences between the signal and background which can be exploited by the machine learning. Not only just look at the single variables, you can also have, if you run this 17, 18, around the block 18 as well, you can also have the differences between the signal and background in the correlation matrix. That means, so this I need to explain here. So the correlation matrix has shown that how the 2 variables, they are correlated, or say, if it's not strictly speaking, how they are depending on each other. And for example, like if you see like this one, the PT of the 2 photon, and the missing T significance is 2 variable. If you see this is a blue color, 0.5, that means they are not highly, but just say intermediate correlated, 0.5. If this value is close to 1, for example, the variable to the variable itself, it is always 100% 1. That means it's exactly correlated. If it's -1, that means like this one. This means the 2 variables, the delta phi between the angle between 2 photon and the PT between the 2 photon, they are anti-correlated. So the issue is that if you observe that these numbers for the signal, this first matrix is for the matrix S, that means for signal. The second matrix is for the matrix B, it's for the background. If you see the number for the same cell, for example, this one, the PT gamma versus the missing T significance, it's 0.51, and this one is 0.2. So this difference, if you only draw the one-dimension histogram, you will never see this difference. But this difference can be taken into account in the machine learning, though it just have very little contribution to the discriminant power, but still there is some. So once you have a few hundreds of the variables or features, that these small differences, all of them can be exploited by the machine learning. So that's why we're using machine learning, but not a single cut, just cut on this figure. For example, on this figure, we can cut on 150, say all of the events smaller than 150, they're background-like. All of the events greater than 150 is signal-like. That you can do, but it's not optimal. That's why we are using machine learning, because machine learning can exploit all of these features from all of these selected features, and also exploit the difference between the matrix, the matrix element in the correlation matrix element. Yeah. Now, okay, we are going to reach basically the training part. So this step, step 19, block 19, and 20, I think it's 20. So these steps, they are what we are trying to do is nothing to do with physics. It's just like a bit of the coding, because we want to, if we want to put the data set into, into the training, we have to merge them in the big one. So, but because at the beginning we know that which data set is a signal, which data set is a background. So this block 19 and 20, what we are trying to do is just a label, add one column in the end of this signal data set, and label every single rows, every single event to be 1. So to say this is a signal. And this block 20, we just label every background events to 0 to label them as a background. And then we just merge them into, I think here, yeah, we merge them into the same data set, because this is just for coding and for the formatting and how we input the data set in the training. Yeah. So now if you go to the block 21, here we are trying to, what we are trying to do is to split the whole data set. Just now we merge the signal and background data set in one big data set is called this data 1. And if we label, say, the last row, last column is called the target. So the target is just this value, 1 or 0, to tell the system, tells the classifier, each event, it is either a signal or a background. Now we don't have the signal and background data set. If you merge them into the big data set, And in the last row of this big data set, we label every single event as a signal or a background. Then here in the second part, this part of this block 21, we are trying to do the training and test split. So this is one of the steps, very, very important step that before you do the training, you have to do so, because that we always have the situation about the overfitting or the overtraining. So if you set up a very super complicated classifier, for example, you have 100 using 100 different features, 100 different 100 hidden layers in the neural network, then after a very complicated training, possibly you will find that a very good performance or the separation power that you split your signal background, but that may not be the correct one, because maybe that the classifier is taking advantage of every single feature which from the random effect or from fluctuation. So this effect come from the fluctuation. Statistical fluctuation cannot be exploited in the third unknown data set because it's total random. So then that's why you need to split at least the training and the test data set. So you use a training data set to train your classifier, to set up all of your weight in your classifier, and then you overlay the results between the training and the test sample. Then you will see that if they agrees well, that means the trained classifier works well. It can predict the correct answer in a new unknown test data set. If you find that the difference between the training and data set is very, very big, usually the training data set will perform much better than the test data set, then that means you have a huge overtraining. That means randomly give you a new data set that cannot successfully distinguish them. Okay. So here that's in this line that we split the whole data set to be the training and the test part, and also tell the last column is called a target for the training, target for the test. And the test size 0.5 is half-half. So we randomly split half of the events go to the training, half of them go to the test. Okay, so this is just some kind of, the last block is just some kind of manipulation in the coding. Then we can just have a look at the data set that you have 7 columns for the training feature, 1 column for labeling the target is signal or the background. Okay, till now that we are going to reach the major part of today of the training. So because we have 2 lectures to cover all of the content, we will stop here somewhere. I will just show the preliminary result of the training. Okay, so firstly here, I'm going to ask, anyone has questions here before we formally go to the training? So I just want to summarize to this step. What we have done is the data set cleaning, labeling the data set, and slimming and filtering the data set to make it be smaller and it looks better and more concise. And also what we are doing is to check the distribution of all of the features to see if they have discriminant power by our eyes, and to see if the distribution looks as our expectation, and also check the correlation between each features for the signal and background data set. Then finally split them to be the training and the test data set. So this is what we have done. All of this is just the preparation before the training. Okay, I see the questions here. What purpose of the stratify? Where is it? I think I saw this word, but I just in cell 23. The current one, this one, 23. Oh, yeah, here. You mean here? Oh, actually, I just forgot that this the feature of this, but I just some kind of setup here. I couldn't answer you this question. This is a very simple thing, I know, just forget it, what's the functionality here. Yeah, basically just you call this function that you set up several arguments here and corresponding to different configuration. Yeah, the next lecture I can just answer this question. I think it's very easy to find out. Yeah. Okay, then if no other question, I'm going to move to the major part of the training. So before that, we are going to set up the training models. So here I just imported several the necessary libraries and for the different method. For example, here, and you can see here what I'm trying to use is 4 different, actually it's 2 different classifier method, 2 different classifiers. The first 3 of them is called the gradient boosting something. It's actually the random forest, or say the boosted decision trees. So I don't know if I think this has been introduced by Deepak somewhere or not. I don't know. That is just one of the major commonly used method, the decision tree. Yeah, is to divide the scenes of population into groups. Yeah, okay, thanks, Noco, that you put some information here. I just forget the details about that that configuration, how you do it. Okay, so I'm trying to say here is, and the first 3 methods this is the most commonly used method in the high energy physics. And this depends on the structure of the data set, because in the high energy physics set, usually you can see that the data set looks like at the beginning, what I'm showing here, you have a very well-defined features and with some float or integer numbers. And each of the weights, each of the rows, they have the roughly equally the weight. Okay, so that's why the decision tree is one of the best methods to do the machine learning for the high energy physics problem. But instead, I also put another method. This is called the MLP, the multi-layer perception. Actually, just the deep neural network, the same thing here. I put another method for the comparison. Later, we will see that how different that these methods they work. Okay, and for the decision trees, or say random forest method, I defined 3 models here. So this 1, 2, 3. So you will find that the 3 models, they are almost the same. The only difference is that the number of, I think this is just the number of trees that's in the forest. So I put different numbers. So the first one is 400, and then the second one is 20, and the third one is 800. Okay, and also the learning rate is same 0.1, and the max steps is that how much steps that you are going to split the decision tree to 2 steps or the 4 steps. Okay, and the others are not very important. So here later, what I'm going to show you is that how is the performance that if you use a different, this is called hyperparameters, that when you build your model. If you use as much as possible the number of trees or the number of the layers or the depths, the splitting depths, then you would have more complicated models. That means it will take a longer time for training, and possibly you will have the better performance than you use a fewer lower hyperparameters. But it is also dangerous if you use a higher number, then you are going to face the high probability of the overtraining. So that doesn't mean that you use the higher this hyperparameter, the better the model. So you have to choose some kind of intermediate value, which has the best discriminant power, and in the same time, the least overtraining. Okay. Yeah. So then if you run at this block, it will take maybe 1 minute. It depends on your machine. It should be very fast. So you can see here for me, that's the first method. It takes 4 seconds. And the second method is take the 200 milliseconds, 0.2 seconds. And the third method, maybe it will take 20 seconds. for my machine. So it takes 15 seconds. And the last one takes just 1 second. So you will see that if you compare the first 3 methods, you will find that you choose a different hyperparameter. It gives you a quite different run time. For example, the first one, 400 trees and the 2 layers of depth, that it just give you 4 seconds. But if you use a much smaller number of trees, then it gives you much smaller time. And the last one, that you use a more complicated hyperparameter, then it gives you longer time. And the last one, this shows a different iteration, and the loss function value is just for the different method. It's for the neural net method to see how that the neural net converging, and finally give you the time. Okay. Then, and because it's already close to the time for today, so what I'm trying to show you to have a good place at where I can stop, I would like to ask you just to run the blocks until here. Yes. Next time I'm going to explain that from the 25 and 26. But here, what I want to show you is just the figures generated by the block 26. So look at the both decision tree, or the random forest, and the neural net output score. So these figures, what I'm showing here is trying to show that how that the classifier can just put together all of the features, all of the input features, and then give you one single one-dimension output distribution. So on this figure, you will see that most of the signal events will be on the right side, and most of the background events will be on the left side. Okay. Yeah. And then your objective is that you hope that the best separation would be all of the blue color go to the right, all of the red color go to the left side. And then what you can see is that you can compare the first figure and the second figure, you will see. Obviously, for the second figure, you have more blue events, or say signal events, which locate on the left side and contaminated with the background. That means you couldn't just use a single card, for example, 0.2, to keep most of the signal on the right and most background on the left. You have to have at least 50% of your signal on the left side as well. So this, you compare the first and the second figure, you can know that the first method and the second method, they have different performance. Obviously, that the first method has better performance than the second, because the second, you have a huge amount of signal, which is contaminated on the left side, on the background side. This is something you don't want. And if you go back to see that when you define this model, you can see that you have 400 trees and a 2 layer of the depths. And this is 20 trees and 2 layer of depths. So the only difference is that the number of trees. Then you know that, okay, 20 number of trees doesn't give you enough separation power for this task, because it's not it doesn't perform as good as you use 400 trees. So this can be obviously see from this one dimension the ability output distribution from here. And if you look at the third figure, that you will see, okay, this figure looks even better than the first one. That means it has an even better separation power than the first one. Obviously, this is because we use a more aggressive hyperparameter, right? So that means till now that the third method, the third configuration of the hyperparameter, that has the best performance for this task. And if you see the last one using the neural net, at least for this case, it seems that the area of the blue on the left side is a bit large than the third one. So that means in this case, the neural net is not as good as the ability which has a very high hyperparameter. Okay, so till now today that we introduced how to set up a framework to do the training using the given well-separated signal and the background data set. And we already have some kind of a feeling that how to understand that the performance of the separation power among the 4 different method, actually 2 different methods, and one of the method has 3 different hyperparameter. So the next time we are going to do some a bit further discussion, how to understand the results and how to select the best hyperparameter and the best method. Okay, I think that we reached today's the time of today, right? Any questions?
Yeah, thank you very much, Xifeng. I think it was an excellent hands-on practical introduction that was really nice. And I think you saw from the questions of the participants that they were really trying hard to catch up and stay active and follow your instructions very closely. I think there is one more question in the Q&A by Noko Cedric.
Is to divide things or population. I think it's a question. This is the answer the first question.
Okay, yeah, sorry, probably, sorry. I just saw something in the Q&A.
I need to check the exact definition of this configuration of this code. This is just very technical things.
Yeah, no, I know that's Python for you.
Yeah,
one forgets all those details, but it's easy to Google them and find out again. Yeah, so it's totally.
This is just a small thing, yeah, technical issue.
Yeah. One can Google it and find it in the documentation quickly. Yeah, I also don't know. Yeah. Are there more questions from our participants?
No more questions.
Comments that they would like to make? You're welcome to use the Q&A or to raise your hand. Okay, if that doesn't seem to be the case, I guess Xifeng people need some time probably to play around a little bit longer on their own, so that they get a little bit more familiar with the data and with your code, and so that they are ready for next week for the next challenge. Yeah. So Xifeng, since there are still no more questions from the audience, I thank you really very much for really an excellent hands-on session that worked out very well. There's always the danger in doing programming live that it goes classically wrong, but in your case, it was classically perfect. So thank you very much. It was really nice. And yeah, and I hope we will see everybody again next week at the same time in probably the same Zoom link. Yeah, but we will send you all a reminder in due course. Yeah, so thank you very much, Xifeng. Have a nice rest of the day and a good afternoon to everyone that was with us today. And please keep staying safe, because the virus is still out there waiting for you to make a mistake. Yeah. So have a good afternoon, everyone. Bye, Xifeng. Thank you very much.
Okay, bye. Thank you. So see you next week. We're going to finish.
Perfect. And I will send you the link for the panelist on Tuesday morning again, so that you don't have to look for it. Yeah.
Okay.
Excellent. Thank you. Thank you very much. Bye-bye, everyone.